Designing for injection molding involves considering factors like wall thickness, draft angles, radii, and material properties to ensure parts are easily and consistently produced. Key aspects include uniform wall thicknesses, proper draft for easy ejection, and rounded corners to avoid stress concentrations. Design for manufacturability and conventional tooling. Per the U.S. industrial standards. Key considerations for injection molding. Design. Wall thickness. Maintaining consistent wall thickness is crucial for avoiding sink marks, warping, and long cycle times. Thinner walls should be no less than 40 to 60% the width of adjacent walls if necessary. Draft angles, or slight tapers on the part's vertical faces, are essential for easy ejection from the mold. A general rule of thumb is 1 degree of draft per inch of cavity depth, but this may vary depending on material and mold capabilities. Radii and fillets. Rounding sharp internal corners and using radii helps prevent stress concentrations and potential cracks. Undercuts, areas that prevent the part from being easily removed, should be avoided or minimized to reduce tooling costs. Material selection. Choosing the right plastic material is crucial, as different materials have varying properties that affect their moldability and final product characteristics. Tolerances. Designers should specify tolerances that are achievable with injection molding processes to ensure the part meets specifications. Parting line. The parting line, where the mold splits, should be strategically chosen to facilitate easy mold opening and minimize features that are difficult to mold. Uniformity. Strive for uniform wall thicknesses and avoid thick sections, as non-uniformity can lead to sink marks and other issues. Ventilation. Adequate venting in the mold is essential to remove trapped air, ensuring a smooth surface finish and preventing defects. Surface finish. Consider the desired surface finish and how it will be achieved during molding, as this may influence design decisions. Design for manufacturability, DFM, is a crucial approach in product development that optimizes design for efficient and cost-effective manufacturing. By incorporating DFM principles early in the design process, manufacturers can streamline production, reduce costs, and improve product quality. This proactive approach ensures that products are easier to produce, assemble, and maintain, ultimately leading to a more competitive and profitable outcome. Here's a more detailed look at why DFM is important. Reduced costs. DFM helps minimize manufacturing expenses by streamlining processes, reducing material waste, and optimizing assembly. Improved efficiency. By considering manufacturing constraints and optimizing design, DFM enhances production efficiency, leading to faster turnaround times and higher output. Enhanced product quality. DFM ensures that products meet quality standards by addressing potential issues early in the design phase, preventing defects, and ensuring reliability. Faster time to market. By identifying and resolving potential manufacturing challenges early, DFM reduces development time and accelerates product launches. Competitive advantage. Manufacturers who embrace DFM gain a competitive edge by producing cost-effective, high-quality products efficiently. Key DFM principles often include standardization. Utilizing standard components and processes reduces complexity and cost. Modularity. Designing products with modular components simplifies assembly, maintenance, and future upgrades. Ease of assembly. Simplifying the assembly process reduces labor costs and improves efficiency. Material selection. Choosing materials that are easy to manufacture and maintain reduces costs and improves quality. Process compatibility. Aligning the design with the chosen manufacturing processes optimizes efficiency. By considering these principles and adopting a DFM approach, manufacturers can create products that are not only functional and attractive but also efficient and cost-effective to produce, ultimately benefiting their bottom line and their customers. Design for assembly. Consider how the part will be assembled with other components, potentially incorporating features like bosses or slots to facilitate assembly. The art of injection molding tolerance, balancing the accuracy and efficiency. Choosing dimension range. By referring to tolerance standards such as DIN 16901, you can determine a suitable size range for specific materials. These standards provide recommended tolerances for different types of dimensions, such as Type A and Type B dimensions. If the material is not capable of holding precision dimensional tolerances, don't expect parts with precision dimensional tolerances. Also, if your molding press is not for precision molding, do not expect the molded part to hold precision dimensions. If the mold is not designed for precision molding, do not expect parts with precision dimensional tolerances for this reason. Know the injected molded material behavior and capabilities and the tool's capabilities, repeatability, and consistency. In essence, repeatability refers to the consistency of results when measurements are repeated under identical conditions, while consistency is a broader concept encompassing the ability to maintain a similar standard or level across different contexts or over time. The repeatability of the consistency of a measurement, expressing how close measurements are to each other, is called A. Precision. B. Accuracy. C. Reliability. D. Validity. The term that refers to the repeatability of the consistency of a measurement, expressing how closely repeated measurements come to each other, is precision. Precision speaks to how close multiple measurements of the same thing are to each other. Accuracy, on the other hand, communicates how close a measurement is to the true value. For example, if you were to measure the length of the same string several times and got values close to each other, that indicates a high degree of precision. Reliability and validity are terms often used in the context of research studies, where reliability indicates the consistency of a method or test, and validity indicates the truthfulness of a method or test in accurately measuring what it is meant to measure. The art of injection molding tolerance refers to the delicate balance between achieving precise dimensions in molded parts and optimizing the overall efficiency of the injection molding process. It involves understanding and managing various factors like material shrinkage, mold design, and process parameters to ensure parts meet dimensional requirements while minimizing cycle times and costs. Here's a more detailed breakdown. Why tolerance is important. Functionality. Parts must fit together correctly and function as intended, especially in assemblies. Reliability. Consistent dimensions ensure parts are reliable and perform consistently over time. Aesthetics. In many applications, dimensional accuracy is crucial for aesthetics, such as uniform panel fits. Balancing accuracy and efficiency. Material-specific tolerances. Different plastics have varying shrinkage rates, so understanding their behavior is crucial for achieving tight tolerances. Mold design. Mold design plays a vital role in compensating for shrinkage and achieving desired dimensions. Process optimization. Adjusting injection molding parameters like temperature, pressure, and cooling time can affect tolerance. Quality control. In-process quality control is essential for monitoring dimensions and making adjustments to maintain consistency. Cost considerations. Achieving very tight tolerances can increase production costs and cycle times. In essence, the art lies in finding the optimal balance between tightening tolerances. This ensures accurate part dimensions, especially for critical features. Streamlining the process, this minimizes cycle times and reduces costs. Understanding material behavior, this helps predict and compensate for shrinkage and other factors that can affect tolerance. By mastering these aspects, manufacturers can achieve high quality, consistent parts while maintaining efficient production processes.